My name's Sam Foreman. I'm a computational scientist here at the data science group at the ALCF. My background is in high energy physics. And now I work on, a lot of, variety of tasks related to training models and running distributed training and the things that come along with it here on our supercomputing systems. And so today I'm going to be talking to you a bit about best practices and tools for hyperparameter management and how, general strategies for organizing experiments and keeping track of the, things as you run them. So just to kind of motivate the reason why some of this is important. So it's by default, it's very easy to fall into bad habits, especially when the things like the tools. So especially when there aren't existing tools and the frameworks, TensorFlow, et cetera, don't take care of things automatically for you. It's very easy to be lazy and save things to, for example, good model and then iterate on that or some variations on that, and then 2 weeks go by and somebody asks you about details of something and it's hard to reproduce, or you can't exactly find the directory, or you don't know what configuration or what options you use specifically for that run. And then, obviously trying to keep track of things when you have a lot of this going on at the same time, obviously can make things complicated. So one way to, maybe do it better than just, randomly choosing names and iterating on them would be to use, for example, something like timestamps. So every time the run is started or something, for example, you can make its own directory and save all of the information and things like that to some uniquely timestamped directory, which is a bit better, obviously, but this is still going to be error prone, and there's a lot of things that can go wrong with that as well. So for this example, or the hands-on portion of this example that we will be doing will be interactive, so it might be worthwhile at the beginning, now I'm talking, to request an interactive job and make sure you're on the system. This doesn't have to, you don't have to actually request 32 nodes, but any suitable choice that will get you through the queue and into an interactive session will work. And similarly for Theta GPU. And so the one kind of main tool I'll be talking or highlighting today is this tool called Hydra. And it builds itself as a framework for elegantly configuring complex applications. And say it's actually probably one of the most useful tools I've used or found and actually use and have taken advantage of in quite some time. And one of the main reasons is that it is very light on, it's very low boilerplate, so that you don't have to repeat yourself and implement a lot of these basic functions to get some minimal functionality. It's also designed to be extensible, so it's very easy to build on top of it and build new integrations and use it in however you might want to customize it for your specific use case. But really at the base level, it serves as a tool for specifying and running experiments and specifying configurations for them. So the key features, again, they're just taken from its website, but are that it provides a hierarchical configuration system, which is composable from multiple independent sources. The configurations can be specified in a configuration file or overridden at runtime from the command line. That supports things like dynamic command line completion, and is primarily used for experiment configuration, execution. There's I think some ongoing work into getting it building out orchestrations and integrations for job schedulers. So I know it has partial support for Slurm, I believe, and Yeah, so it's, very active development and undergoing a lot of new changes and new features being added. So the kind of example we will cover here is somewhat simple, but should be enough hopefully to give you an idea of the basic functionality and demonstrates, hopefully it'll illustrate some of the ways that you could use it beyond the scopes that's covered in this tutorial. And so they have tutorials online in their documentation as well, which is, very good and provides a lot of examples. But it's easiest to kind of get to know things by trying them out and kind of, seeing how they work. So to install it, all you need is this Hydra core library, which is by default installed in the base environment of Conda on Polaris. But it also worthwhile is installing this Hydra color log, which gives you nicely printed logs and things like that. And it's a pretty minimal library package. So the most simple example, just to kind of give people an understanding of how, or an idea of how it all works. So we define here some very simple application, right? We just have this one simple main function whose goal is to print in the as a YAML string the configuration that it receives. So if you were to run this application with these command line arguments, so if you specify, so one thing that's worth mentioning here is that there's no configuration files or anything, so you can dynamically just create these options at runtime. So if you were to run this application right here with these command line arguments, it would output the following YAML string. And so you can see that they automatically get nested. Fields are automatically nested at periods. And so it's useful if, for example, you have, want to pass in something that either isn't defined in your configuration or you don't have a configuration file at all in the first place. So that's the kind of simplest, most straightforward example to demonstrate the minimal functionality. But this obviously doesn't really do anything, so it isn't very useful. And so a better, slightly more complicated example would be to define a configuration file. So if, for example, in your working directory, you have some configuration directory, and within that a file called config.yaml, and also within your current working directory, you have this file called main.py containing the same application that we saw on the previous slide. Basically, it will just take whatever it takes in this dict config object, which Hydra kind of automatically builds and populates, and it will just print out whatever it receives. And you need to make sure, in this case, to wrap. You need to have this conditional clause. So when you run this application from the command line, the actual main function gets executed. And Hydra will basically use this to pop. This wrapper on the main function will only be executed if Hydra it detects it's running from the command line. So you need to make sure to include that executable block. And then, essentially, I thought I had more saying about the output, but in essence, this would again just print out exactly the YAML string that it automatically parsed, in this case, from the config. Oh, and so the thing I had forgotten to mention is that we specify the default path for our config object in the wrapper on top of the main function. So in this example, it will look in the path or in the directory configure in the conf directory and look for a YAML file with the name config. And so doing this, at least now this is a minimal idea of how you can get things to work. And so you can imagine extending this beyond just specifying parameters in your network, for example. You could also add additional things, like related to the data sizes and really a whole host of things. Anything that your experiment needs to be configurable, you can build out through a series of nested configuration files, which can then be overridden dynamically on the command line as needed. And all of these configurations kind of get parsed internally by Hydra and put into this dict config object, which you can then use inside of your code. So the next thing I want to talk about, at least in the slide portion, is how you once you have a system and a means for running experiments and specifying the configurations that you need to be able to run them. The next important part is to have some metrics that are useful for determining the performance of your model, right? So when you're running an experiment, naturally, the idea is that you change some parameter or you change some setting, and you want to see how that impacts some downstream tasks, say, for example, model performance. And in that case, you have some metric that essentially quantifies the performance of your model or whatever the downstream task may be. Maybe it's money raised or things like that, depending on the use case, but you have some quantifier that you use to determine the quality of a given experiment, for example. And so you want to be able to track this quantity then obviously across multiple experiments and see how changing different things has the ultimately impacts the downstream tasks. And there are a lot of actually, a real lot of companies these days that are looking to provide services in this space. One of them, probably maybe the most widely known or used, is called weights and biases. And so I think it's actually been touched on in a bit in some of the earlier talks here as well. So maybe people are familiar with it and pretty well known. So maybe people have seen it independently as well. But they're kind of, I guess their big goal is to be the machine learning platform for developers to build better models faster. And so they really do a pretty good job of implementing functionality that makes developers' lives easier. So they, for example, offer services like experiment tracking, which allows you to visualize experiments and see metrics in real time. Things like they also offer hyperparameter services, which helps you obviously optimize models quickly and find the ideal set of hyperparameters that you're interested in. Things like data and model versioning, model management, collaborative reports. So one of the other kind of nice features is that you can, going directly from the workspace that you have in weights and biases, you can kind of pull figures out of that and add them to reports, which are then shareable and with others, and they get the advantage of having these interactive diagrams. And you can see things without having to point your colleagues to some obscure folder or file location in the system. You can just send them a link and they can see it directly. And it also has built-in integration for most of the major frameworks and tools that are out there, and they are constantly working on developing and adding more. So if your favorite integration isn't supported currently, it will be soon, I would imagine. And if you were to ask, I'm sure that they would be happy to try to help you get it going. So the tool or the stuff necessary to get started and logged in are pretty straightforward. And it's installed by default in the base content environment on Polaris, so this is a bit unnecessary, but for the sake of completion, you can install it just using pip and then log in using this weights and biases login, which will, I think, point you to it will output a web URL that you can then log in. I think Huiho actually in the tutorial earlier mentioned that you can also set an environment variable that specifies your API key, which is also has the same effect. And so then once you're kind of logged in and authenticated, all you need to do to get it up and running for your experiment is to call this init function inside your code, preferably inside the main loop. So you would want to do this at the top level, and then once this run is initialized, you can then track any metrics that you're interested in just by passing for example, a dictionary to this weights and biases log function. So I have included here some graphs just showing some metrics from some experiments I ran earlier on the code in the associated GitHub repo. And so you can see, for example, you can track things like the loss for multiple different experiments, as well as things like the accuracy and a whole bunch more as well. And so you can obviously then go back and see what the details are of each of these experiments, and see what the differences are, and get an idea of what changes led to, in this example, this maybe the model improvement between this run that seems to have done quite poorly versus the rest of them. And so the next kind of level up from tracking individual experiments manually, kind of by hand like this, and looking at differences between individual runs and things like that, what's usually more useful or productive is to do some sort of hyperparameter optimization, where you specify the different possible values of the different configuration options that you want to consider, and deploy some process that will essentially try all of those different combinations, either in sequence or in parallel. And there are also a lot of different tools out that offer hyperparameter optimization. So DeepHyper, for example, is built here at ALCF, and a very good library, but it's been covered a lot in previous tutorials, and there was a workshop over the summer. So anybody who's looking for more information on that, I can send the link in the Slack channel, but that is one of the maybe most easiest to get up and running tools that we offer and support here at the ALCF, but there are also a variety of others. And so there's definitely no shortage of tools that you can use if you want to do it. Sticking with the weights and biases theme for now, they offer this kind of nice plot, which is maybe a bit confusing, but hopefully I can try to parse some of it for you. But the idea behind this is that essentially each individual line in this plot corresponds to a single experiment, and the points that the lines go through correspond to the options or the configuration options of that experiment. So I don't know if you trace, they get a bit hard to follow here without them being interactive, but if you were to for example, trace this blue line back, say it maybe went through, had dropout weight in the first layer, 0.2, 0.2. And so on the actual weights and biases webpage, it's a bit easier because these are highlighted and dynamic. So you can kind of see them as you scroll over them. But the basic idea being that each of the different lines corresponds to a different experiment. And you can see which hyperparameters that experiment used by seeing which line or which of these points the line goes through. And then all the way on the right, you have some metric that you're interested in, for example. So in this case, I have both the loss and the accuracy included. And you can see that, it actually, so this is for the fashion MNIST data set, in case you're curious, but you can see there's actually a pretty big range in accuracies. And so, going between the worst and the best model and across these experiments, there's 11% or so increase in accuracy. So this was a pretty straightforward, simple example. So you can really kind of see how doing this in a reproducible, easy to follow and track, using best practices can really be advantageous and reduce the amount of headaches that you face. And so, as I mentioned earlier, these results can then kind of be aggregated and put into a report, which you can then share on the web. And so again, you can see, so I should come to this, but you can see here, for example, there's the same plot from the other slide, where each of these different runs again corresponds to different experiments. You can see, for example, the options that each of these different experiments actually went through. and how they ultimately ended up doing on the test accuracy, for example, in this case. And yes, so this is a report which basically allows you to kind of aggregate things, pull things in from different runs. You can like select different runs all in here interactively, which is really nice, and lets people kind of play with things and do their own sort of analysis on things. And are obviously much easier to share than even Jupyter notebooks and things like that, for example. So they are a really big company, and for the sake of time, I'm not going to go over this, but they're actually working on a lot of really cool new features. This, for example, is new Weave library, which actually looks pretty cool, but I will not have time. I'm not going to go into too much for the sake of time, so I can get through everything. But again, all of this are in these slides, and I'll send the link so everybody has access to them after this. Or they're also available online, so if you can see the URL, you can follow along. And so there are a lot of this. So the purpose of this talk focus mainly on weights and biases, but these sorts of tools and offerings are definitely not unique. So there are a lot of other companies that are working on providing similar functionality. So DeepHyper, for example, was originally started as a hyperparameter optimization library, but I know that they are currently working on building a dashboard like backend for things like this, so you can see how runs perform and things. TensorBoard, which was kind of the first in this space, maybe, but that's still around and very widely used. Other tools like AIM, I don't know, ZenML, Sacred, MLflow, Determine.ai are other ones, and they all have kind of their own unique advantages and disadvantages. But if you're interested, some of them are definitely worth exploring and trying out. And most of them are pretty straightforward to get set up. So the amount of code modifications needed to try some of them out is pretty minimal. And so this is a pretty actively growing area of software research, software production, I guess, even research actively. So weights and biases, for example, it just raised $135 million. And they just announced relatively recently new partnership with NVIDIA, who also I think raised them some seed funding. So it's definitely a growing field of area that people are exploring. And there's a lot, many different ones. So there's this website, MLOps.toys, that kind of aggregates them, and so you can scroll through there and see some of them. But so now I will, maybe if I do that. So we will then now go back to the GitHub repo. So hopefully everybody has this cloned and is up to date. If you don't, then I suggest you should clone it and make sure you do a git pull so that everything's up to date. And we are going to be looking at this hyperparameter management folder. So there's some additional information on things here. So for example, there's this README that has some, I think I have some changes in my local and my fork that aren't, I'll have to push them to the GitHub or pull them into the new one after this. But so I will have in the SDL workshop repo. So this is just the README, the code is all the same. But there's some differences in here, so I'll use this one for now. As I mentioned earlier, we look at using Hydra for configuration management. There's some information here about how to get it installed and running, and some additional information on how things are formatted and kind of what the data objects look like behind the scenes. And so one thing I actually didn't touch on in the slides, but might be maybe worth mentioning now, is that we saw in the slides, for example, you can configure And you can define your experiment configuration using a YAML file, for example. In this example, we just looked at a very simple case of just a single network option with these three nested hidden size, activation time, dropout rate. But you can imagine expanding this and going to include multiple different things. So like for the things that specify options about your data or your training, for example. And one of the kind of really nice things about Hydra is that you can then define objects which tell Hydra how to actually instantiate them so that you can get statically type checked configurations as well. And so, for example, within the hyperparameter management folder, there's this configs.py file. And for each of the options that I have specified in my config, I can back it by a data class object, which tells Hydra how to instantiate it. And so the network config, for example, you can just create a data class that specifies that this first argument or the value of the argument corresponding to this drop1 parameter should be a floating type. And so that ensures that all of the types of everything are consistent, and it will raise an error if you try to basically pass it something that it doesn't accept. And so the details of this are maybe a bit involved for the sake of this workshop, but yeah, so the code is, I've tried to make it pretty straightforward and easy to follow, and it's obviously all available on here as well. So people can look through it, and obviously feel free to let me know if you have any questions about anything. But so each of these, and so the main idea being that each of these configuration objects are then kind of specified in this one main configuration file. The specific Python instance that Hydra will try to instantiate it into is specified by this target field with underscores. So that's kind of a bit of a subtle detail, but might be important if people are confused about where this is coming from. And then within this, you can basically specify a list of defaults. So for example, I can specify that I want to use the default configuration for the network, the default configuration for the data, the trainer, etc. These are additional Hydra, actually just Hydra specific, so aren't necessary to understand to get things running. Really, all you need to know is that we have some set of defaults. We specify the network, data, trainer, and the weights biases configuration. And Hydra will essentially load all of these by default at a base point, and then work to instantiate them using the Python objects specified by their target fields. And so this one thing that's really kind of nice about this is that it lets you run things either just straight as they are using the defaults without any modifications, but you can also override them manually from the command line, for example. So I've included this in this repository. There's this train.sh script, which will basically do everything that you need to run distributed training on a simple convolutional neural network. And yeah, you can specify a different command line. So for example, if we wanted to make sure to load and activate your conda module, and then from within this hyperparameter management directory, I would recommend installing, creating a mini virtual environment and installing it within that. So I've already done that, but for this purposes, the command to do it would be like that. So Python and create a virtual environment, which I'm not going to go into. I think that's already been covered, and if not, the documentation for it is on the website. So you'd want to create a virtual environment first and then activate it. And then you could, for example, do a local editable install of the project, which hopefully this should just say it's already everything's already installed and not give me any issues. Also, if anybody has any questions, I've seen the Slack notification ring a couple times. So if anybody has any questions, feel free to stop me here. Interrupt as at will. I know it's already installed. I'm not gonna let it finish for the sake of time. But that would just, basically go through and make sure that you had all the required libraries needed. And then, so once you're in here, you can run this training script, and by default, it will use the configuration specified in this configuration directory if nothing is manually overridden. And you can see that it'll automatically, so this training script will automatically, using Torch DDP, pick up on the number of available GPUs and initialize DDP to use all of them. Oh yes, there it goes. Print some additional information. So for example, you can see that there are 2 ranks, 4 GPUs on each of those ranks. For 8 GPUs total, which Python we have, the MPI we're running, and then the full executable that will be ran. And then you can see weights and biases gets initialized and gives you the URL to see your run online. Oh, let's see. Okay, so within this training script, it actually writes it out to a separate log file. There we go. So yeah, again, all these commands are actually everything needed to run it is included and described in the README on the GitHub repo. So don't worry about if you didn't follow those commands explicitly. Yeah, essentially it's just launching the training script. And you can see then it starts and launches the training. Some warning, but you can see it's using all the available 8 GPUs, running for 2 epochs. Pretty straightforward. Yeah, I guess I can actually let it run for a minute and wait and pause and see if anybody has any questions about anything.
Sam, there was a question about, I think this was back during the weights and biases talking about hyperparameter search. Are they doing some kind of hyperparameter search algorithm, or is it trial and error?
So that was going to be the next thing I was going to touch on. I realize I'm running a bit long, but is there what does the rest of the agenda look like? It's scheduled for the breakout rooms following this talk, right?
Yeah, sorry, just bringing up the calendar.
Sorry,
So we have 4 minutes left and then breakout rooms, so people can
Okay.
ask more advanced questions during the
Okay, that's
breakout
what
rooms.
okay, all right, that's what I was gonna say. Sounds good. Yes, so yes, as Bethany was mentioning, everything I've talked on so far it still involves running. This is still individualized, right? So you run a single experiment, and with some set configurations, but obviously this is not ideal, especially when you want to find, for example, the optimal set of hyperparameters for your specific problem. But we at this point really have all of the necessary infrastructure to take advantage of any different number of hyperparameter libraries. So they all have different, I guess, kind of trade-offs. There are advantages and disadvantages to all of the different ones, I imagine. Weights and biases obviously has the advantage of being integrated with weights and biases and can pull from all of that existing data, but there is definitely support, and it is relatively straightforward to try out different ones using the kind of infrastructure that is laid out in this project, or that you get from using Hydra and some additional best practices. So while that's running, I will go in and talk a bit about this. So one thing I haven't touched on yet is inside this configuration directory, we also have this additional nested sweeps directory, which has a bunch of different YAML files. So if we look at this max accuracy distributed YAML file, we can get some intuition for what it's trying to do. So it has you can specify the name of this hyperparameter sweep, the method that you want to use. So this is specific to the weights and biases sweeps for now, but the advantage of using Hydra for configuration management is that it doesn't take any additional effort on your part, because you already have a series of configuration objects, and so it's very easy to then add an additional configuration object that represents the range of hyperparameters you want to consider, for example. And so in this case, we can look at like the trainer, the learning rate, the initial learning rate. You can specify values as some set of choices, or you can use the min and max, which will look over a continuous range. There are also additional options for specifying things like the distribution over which these different values are sampled, and things like that. But one of the other kind of nice things, and I realized it just turned 3, so I'll wrap this up now, but is that you can specify an arbitrary program to execute, and what weights and biases will do, for example, is sequentially run individual experiments corresponding to some set of parameters specified in your configuration file, and it will run whatever is specified by this program field here, and we'll try to maximize whatever metric you specify here. And it doesn't just use, in this example, it just uses simple Bayesian optimization. So it will try one example and then kind of, go in the opposite direction and kind of sequentially update things. And as you saw earlier, that can obviously then be used to see how all of your different experiments compare to each other and things like that. So for example, here, as you can see, how each of these different runs ultimately did as measured by the accuracy or the loss, for example. And so there's obviously a lot more in here than I have time to get into now. And so for the sake of wrapping it up, and then people take a bit of a break, I'll wrap it up now, but I will obviously be around, and I'm more than happy to take any questions anybody has about anything or anything like that.